In this video, we're going to look at aldehydes and ketones, some oxidation reactions that can be used to form aldehydes and ketones, and then we're going to look at some of the properties of aldehydes and ketones. Similar to what we did with the alcohols, thiols, and ethers, you do not need to know nomenclature for these functional groups. However, you will have to be able to identify them. An aldehyde or a ketone consists of a carbonyl group. A carbonyl group is a carbon that's doubly bonded to an oxygen. You are going to have a partial positive on the carbon and a partial negative on that very electronegative oxygen atom. There are also two lone pairs on the oxygen atom of a carbonyl. So there's a very strong dipole in an aldehyde or a ketone. In an aldehyde, you are going to have a carbon on one side and a hydrogen on the other of that carbonyl compound. So here's my carbonyl. For an aldehyde, you have a hydrogen on one end. For a ketone, then the carbonyl will be bonded to two alkyl groups. You may see an aldehyde written as CHO. The double bond is implied. In a ketone, the carbonyl group is bonded to two alkyl groups and can sometimes be written as CO, but that's less likely because we don't want to confuse it with an ether. All right, so again, in a condensed structure, you might see an aldehyde represented as CHO. This is pretty rare to see the CO written that way in a ketone, but you have to be able to recognize an aldehyde in a bond line structure or a ketone in a bond line structure. So I'm going to skip through no nomenclature. So you don't need to know any nomenclature of aldehydes and ketones. I'm not even going to have you worry about the suffix, the end of an aldehyde or a ketone. You just need to be able to identify that functional group in a molecule. Aldehydes and ketones can be soluble in water. They can form hydrogen bonds with water through that carbonyl oxygen, where they can accept a hydrogen bond here because you have the two lone pairs on the oxygen. They are very soluble when they have 4 or fewer carbons, but not soluble when they have longer hydrocarbon chains. So similar to alcohols, as we increase the length of that nonpolar hydrocarbon chain, we diminish the solubility in water. So similar to what we looked at for alcohols, here's a table of aldehydes and ketones with different numbers of carbons and their solubility in water. Let's go through some important aldehydes and ketones. Acetone is a solvent that's used in nail polish remover, cleaning fluids, and paint. It's a very useful organic solvent because of the polar carbonyl group and the non-polar methyl group. So it's got that duality that ethanol has. However, it's more volatile than ethanol. It evaporates more readily. So when we want the solvent to go away quickly, acetone might be a better choice than ethanol. Formaldehyde, which is the simplest aldehyde, is a colorless gas with a very pungent odor, and it is used as a solution to preserve biological specimens. It's also used in embalming fluid during the preservation of a dead body. Here are some other important aldehydes and ketones. We have benzaldehyde, which is responsible for the almond flavor. We have vanillin, which you can see here has not only an aldehyde, but it has an ether and an alcohol group. So vanillin is a really good example of what you're going to have to do with these functional groups. I'm going to give you a molecule on an exam, and I'm going to tell you to identify the key functional groups. So if you were given a structure such as vanillin, you would need to identify the aldehyde, the ether, the OH group, and the benzene ring. Or you could just say, I'm just going to change my color, you could identify this as a phenol. Right? So that's the type of things that you need to do with these functional groups. In cinnamaldehyde, okay, what we're going to see is you have a ketone, you have an alkene, and you have benzene. So let's classify each molecule as an aldehyde or a ketone. A is a ketone, B is an aldehyde, C is an aldehyde, and D is a ketone. Now we're going to look at reactions of alcohols, thiols, aldehydes, and ketones. We're going to learn to write a balanced chemical equation for combustion, dehydration, and oxidation of alcohols. The products of these reactions will be aldehydes and ketones. Alcohols undergo dehydration when heated with an acid catalyst. The loss of hydrogen and OH from adjacent carbons produce an alkene and water. So if you remember when we were in the alkene chapter, we did hydration reactions, and that led to an alcohol product. And if you remember, the OH added to the carbon with more carbon atoms. So now when we have an alcohol, we can dehydrate that alcohol when we use acid and heat to give us an alkene product. When we learned about oxidation and reduction reactions previously, we learned that oxidation is when you lose electrons, and when you have a reduction, you gain electrons. We also learned that these reactions go hand in hand. You can't have an oxidation without a subsequent reduction. In organic chemistry terms, oxidation reactions increase the number of carbon-oxygen bonds by the addition of oxygen or a loss of hydrogen atoms. For reduction reactions, they reduce the number of bonds between carbon and oxygen atoms, or you gain hydrogen atoms. Alcohols undergo oxidation, which increases the number of carbon-oxygen bonds. So if we have a primary alcohol, and again, remember, primary alcohol, here's your alpha carbon. That means that there is one other carbon bonded to that alpha carbon, will be oxidized to produce an aldehyde. And here you can see our aldehyde. We can take aldehydes and further oxidize them to produce a new functional group called a carboxylic acid. I briefly introduced you to this group in the alkene chapter when we were looking at saturated and unsaturated fats. We will learn more about this in subsequent chapters. I want you to just recognize for now that a carboxylic acid has a carbonyl and an OH. The entire group is a carboxylic acid that's in the red box. You can see that it's an oxidation because we are increasing the number of carbon-oxygen bonds. Here you have a carbon-oxygen double bond, and then when we oxidize further to the carboxylic acid, you can see that we've made a new bond between the carbon and the oxygen of the hydroxyl or OH group. Secondary alcohols are oxidized to produce a ketone. So let's just look at this alcohol here. And it's a secondary alcohol. This is our alpha carbon. It is bonded to two other carbons. When we oxidize this secondary alcohol, we are going to increase the number of carbon-oxygen bonds. And you can see here now that we have a carbon-oxygen double bond. Ketones are the final state for a secondary alcohol. Our ketone does not get oxidized further. Tertiary alcohols do not readily oxidize. If we look at our alpha carbon, it is tertiary because there are 1, 2, 3 carbon groups bonded to it. You cannot lose a hydrogen here. So there is no oxidation product for a tertiary alcohol. Methanol is also known as methyl alcohol. It is highly toxic and found in windshield washer fluid, sterno, and paint strippers. It rapidly absorbs and is oxidized to formaldehyde and then formic acid. So here's our methanol. We can oxidize it to formaldehyde. Formaldehyde has 2 hydrogens with that carbonyl. You have a further oxidation to methanoic or formic acid. Here's that carboxylic acid functional group. Formic acid is not easily eliminated and leads to metabolic acidosis and end organ damage. Formic acid will disrupt oxidative phosphorylation due to formate's inhibition of cytochrome oxidase. We'll learn about oxidative phosphorylation when we learn about biochemistry in later chapters. Ethanol acts as a depressant and kills or disables more people than any other drug. Consumption of ethanol can be analyzed by using a breathalyzer. Ethanol is metabolized to acetaldehyde and then carbon dioxide and water. So if we look here, we have ethanol. It's a primary alcohol. The first oxidation will make acetaldehyde. You can see your aldehyde functional group. Subsequent oxidations are going to produce carbon dioxide and water. So just to show you the structure of carbon dioxide, you can see we've increased the number of carbon-oxygen bonds. Now we're going to look at a thiol. A thiol, if you remember, is an SH group. Thiols can undergo oxidation. The hydrogen atom is lost from each of the two sulfhydryl groups. The product is going to be a disulfide. This is a very important biochemical reaction. Protein in hair is cross-linked by disulfide bonds found in the amino acid cysteine. We'll learn more about this when we learn about amino acids and proteins, but cysteine has a free thiol group. When it is oxidized, you lose a hydrogen and you form this disulfide bond. This is the basis for perming and keratin treatments. You disrupt the disulfide bonds that are present in hair. When we learn about carbohydrates, we will see that simple sugars may have a free aldehyde group. Tollens test is a test which oxidizes aldehydes but not ketones. Tollens reagent contains silver plus cations that are reduced to metallic silver in the presence of an aldehyde, so that you will get a mirror coating on the inside of a test tube if aldehydes are present. So here's your aldehyde. If you put it in the presence of silver ions, you'll have an oxidation reaction where silver is reduced and acetaldehyde is oxidized to acetic acid. Again, this is our carboxylic acid functional group. In Benedict's tests, Benedict's reagent contains copper 2 plus ions, which will react with aldehydes that have an adjacent OH group. This is also an important test for sugars because we will learn that carbohydrates are polyalcohols, where they have multiple OH groups. When Benedict's solution containing copper 2 plus copper sulfate ions is added to this type of aldehyde and heated, a brick red solid of copper oxide forms from the aldehyde. The test is negative with simple aldehydes and ketones. So again, this is a good test for sugars because sugars have an OH group adjacent to an aldehyde. So if you have your aldehyde and an OH group adjacent, you add copper 2 plus cations, you are going to get a copper oxide, right, where you get a reduction, and then you are going to get an oxidized organic product. Here's your carboxylic acid. So you can see this colorimetrically here. And again, this is what I was talking about with the carbohydrates. This is D-glucose. This is the predominant form of glucose found biologically. Here's our aldehyde, and here is our adjacent alcohol. So in the presence of Benedict's solution, which has copper 2 plus ions from copper sulfate, we are going to have an oxidation of glucose and a reduction of those copper ions. And therefore, we are going to get gluconic acid and this brick red solution of copper oxide. All right, so now we've looked at oxidations. We're going to now look at reductions of aldehydes and ketones. And remember, with a reduction, we are gaining hydrogen or losing oxygen. In the reduction of organic compounds, aldehydes and ketones will be reduced by sodium borohydride or hydrogen. We saw this type of reduction with hydrogen when we looked at alkenes to alkanes. All right, I just want to keep making those connections for you. Here, the number of carbon-oxygen bonds is reduced by the addition of hydrogen or the loss of oxygen. A catalyst such as nickel, platinum, or palladium is needed for the addition of hydrogen to the carbonyl group. So this is going to be very similar to that alkene to alkane reaction. When an aldehyde is reduced, it will form a primary alcohol. So here is our aldehyde functional group. We are going to add hydrogen in the presence of this metal catalyst, and we will form an alcohol. It's a primary alcohol because your alpha carbon is only bonded to one carbon. Here we have a ketone. When a ketone is reduced, it is going to make a secondary alcohol. So this is my ketone functional group. This is my secondary alcohol. The alpha carbon is bonded to two carbons. Let's do a learning check. Select the product for the oxidation of the following. Okay, so what I want you to do is look at the starting material. You should be able to identify that it is an alcohol. Next, I would identify what type of alcohol. Is it primary, secondary, or tertiary? And you should see that this is a secondary alcohol. Here's C alpha, we have 2 carbons. This is an oxidation reaction, so we need more carbon-oxygen bonds in the product. Also, it's a secondary alcohol, so we should be looking for a ketone product. So this will allow us to eliminate A. This will allow us to eliminate C. And we are left with B and D. Well, we can eliminate D because that is an alcohol. So the only possible answer choice is B. That is the only ketone that is present. Now, let's do another learning check. We need to select the product when the alcohol shown undergoes each of the following reactions. So again, let's look at this alcohol. We should be able to see that it is a primary alcohol, and it is going to undergo 2 oxidations. The first oxidation should lead to an aldehyde, and the second oxidation should lead to a carboxylic acid. All right, so for the aldehyde, that would be choice 3, and then for the carboxylic acid, that would be choice 4. I'm going to go through this problem with you just so that you understand it. However, you will not be responsible for this where you have 2-propanol. You might have some homework problems where you're given the name and then you have to draw the structure. However, you will not be responsible for nomenclature on your test. When you're doing homework, you can look up the structure for these names. So give the primary product for the reaction of 2-propanol when it undergoes oxidation. So propanol has 3 carbons. 2-propanol means that the OH group is on the second carbon. Okay, so for an oxidation reaction, we are going to form a ketone. For a dehydration reaction where you remove water and you have H plus and heat, we are going to form an alkene. Okay, so you do not have to draw this on your exam from a name. However, if you are given a structure on your exam, you would be responsible for drawing the products of those reactions. Okay, so this just shows you, here's 2-propanol, here's the product. Now, I didn't balance the reaction. I wasn't asking for a balanced reaction here. I just wanted the products for the reaction. Okay, so here it says, write the structure and name of the organic product when each is mixed with Tollens reagent. I did not go through nomenclature of aldehydes and ketones. I didn't go through anything as far as the suffix goes. So you would not be responsible from this on the exam perspective. But again, if you have homework problems assigned to this, I figured it takes you a little bit more time with the homework anyways, because that's supposed to be your difficult practice. So for butanal, that is an aldehyde. And the structure looks like this. There are 4 carbons. So that's A. Acetaldehyde has 2 carbons. And then we have ethyl methyl ketone. Okay, so now what you need to do is write the structure and name of the organic product when each is mixed with Tollens reagent. I just want the structure of the product. So for A, we have an aldehyde. If you remember, Tollin's reagent is that silver plus ions. So we will make a carboxylic acid with 4 carbons, 1, 2, 3, 4, plus silver metal. For B, we will form acetic acid. Again, you don't need to know the name, but you should be able to draw the structure. Plus silver metal. And for C, there should be no reaction because Tollin's reagent does not react with ketones. All right, so this concludes the chapter about alcohol styles, ethers, aldehydes, and ketones. Okay, so from the nomenclature perspective, you do not need to name alcohols, but you need to recognize that the OL means that you have an alcohol. So that suffix means that the alcohol is the primary functional group. You need to be able to identify a primary, secondary, or tertiary alcohol. You need to be able to identify an aldehyde, a ketone, a thiol, and an ether. You need to understand the properties of these molecules, that alcohols can hydrogen bond, ethers can accept a hydrogen bond, but they cannot donate. You need to understand how this manifests itself into intermolecular forces. So for example, alcohols will have stronger intermolecular forces than an ether with a similar molecular weight because you have more hydrogen bonding capability. Therefore, you have a higher boiling point. You need to know reactions of these molecules. So you need to know dehydration and oxidation reactions. You need to know how to reduce an aldehyde to a primary alcohol and a ketone to a secondary alcohol. For your thiols, you need to know about the formation of the disulfide bonds, which is an oxidation reaction.